Good scores do not guarantee a good ranked list. I'll compare Pointwise ranking with LambdaMART in LightGBM so you can train for the metric users actually feel. This is the setup you'll be able to run after this, which compares Pointwise and listwise training and returns the better ranked list by your chosen goal. I'm Professor Pi, teaching AI foundations with simple Python. Ranking matters because users care about the ordered list they see, not a single score. Search, recommendations, and ad ranking all care whether the best items appear at the top. Pointwise models learn to predict a relevance label for each item. LambdaMART learns to order items so metric gains improve where users look. Choosing the right approach can change which item lands first, and that can change clicks and revenue. Intuitive level. Think of Pointwise like rating each dish on a menu. Listwise is like arranging dishes so the best ones sit at the top of the menu. Pointwise is simple and flexible. LambdaMART is more focused on the ranking goal and can prioritize the top of the list. The trade-off is that listwise training needs group information and different losses. We will build a tiny, repeatable example. You will create a small query and document set, fit a pointwise regressor, measure NDCG, which measures how good the top of the list is, then train a LambdaMART ranker and compare. Finally, we will tweak how much the ranker cares about the very best items. This keeps the code short and the behavior obvious. Now we will create the toy data and fit a pointwise model. This snippet creates a toy query document dataset and fits a LightGBM pointwise regressor. A random generator makes a small feature matrix X and query IDs Q with 3 queries and 4 docs each. The labels Y are constructed per query by scoring features with a hidden linear rule and marking the top 2 documents as relevant. The model MReg is a LightGBM LGBMRegressor, trained to predict these graded labels from features. Using a small number of trees and shallow depth keeps the behavior simple and prevents instant overfitting on such a tiny dataset. The printed counts confirm we have a compact, reusable setup for later ranking comparisons. Next, we will evaluate ordering quality with a concrete metric. This example evaluates Pointwise LightGBM scores with a query-wise NDCG at 3 function. The helper NDCG at K groups documents by query IDs Q, sorts them by predicted scores, and computes discounted gains using the standard 2-square relevance -1 mapping. It also builds the ideal list per query to form a normalized ratio, then averages across queries for a stable overall metric. The predictions come from the LightGBM LGBMRegressor via mreg.predict, showing how pointwise loss translates into list quality. Increasing K will reward broader ordering quality, while decreasing K emphasizes just the very top. The printed NDCG at 3 reflects how well pointwise training orders the first 3 results. Now, we will train a LambdaMART ranker that optimizes list quality directly. This code trains a LambdaMART LightGBM ranker and scores lists with NDCG at 3. The vector G holds per query group sizes for the training data. The model MRrank uses LGB.LGBMRanker with objective.LambdaRank, so its gradients directly optimize pairwise swaps toward higher NDCG. After calling mrank.fit with the group information, we predict list scores and reuse NDCG at K to compute a comparable ranking metric. Adjusting N estimators increases model capacity. Larger values can improve fit, but may overfit if features are weak. The final printed NDCG at 3 reveals how optimizing a list-wise aware objective can better align training with ranked list quality. Next, let's inspect what each model picks as the top document for a single query. This snippet contrasts top 1 picks from Pointwise and LambdaMART on one query. It selects query 0 by slicing the shared feature matrix X and evaluates both mreg predict and mrank predict over those 4 documents. Using arcsort, it finds the highest scoring document per model and maps each back to a global index. The label array Y then reveals the actual graded relevance for each top choice, letting you see whether the pairwise objective found a stronger first result. If you trained the models with deeper trees, both might converge to the same best item. The printed gains make the difference at rank 1 immediately visible. Finally, we will push LambdaMART to care more about the very top by changing its gain structure. This example tunes LambdaMART gains to emphasize top ranks and measures top 1 hit rate. The model M-tuned is another LGB.LGBM ranker using objective LambdaRank, but with label gain equals 0, 1, 3, 7, giving higher utility to the highest relevance. After training with the same group data, predictions are scored by checking whether each query's top result hits the max relevance. The loop aggregates hits across queries and averages them into a simple top 1 rate. Increasing label gain contrast can push the model to favor the best item even more, sometimes at the expense of deeper ranks. The printed rate shows whether tuning improved the very first result. In a real system, this maps to using your query logs and feature store instead of the toy matrix. You would group by query session, derive features per item, and run the same compare procedure to see whether list-wise training improves clicks. The toy flow shows where to plug in real features and how to interpret NDCG and top 1 changes. Recap. It is a comparison between a Pointwise regressor and a LambdaMART ranker for producing ranked lists. Use Pointwise when labels are noisy and you need a simple per-item predictor. Use LambdaMART when the ordering and top ranks matter most. Caveat. List-wise objectives need correct group information and can overemphasize top items if games are set too aggressively. Next step. Tune the LambdaMART label game contrast to push the model toward better top 1 accuracy. And watch how NDCG and top 1 behave. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.